On October 6th, the Royal Swedish Academy of Sciences awarded the 2021 Nobel Prize in Chemistry to Benjamin List and David Macmillan for the development of asymmetric organocatalysis. For the uninitiated, that can almost sound like gibberish, so let's break it down. In order to understand this discovery, you need to know what a catalyst is. A catalyst is a substance that drives a chemical reaction without participating in it. All chemical reactions have what's called an activation energy, a threshold that must be reached before the reaction can proceed. Catalysts lower this activation energy, making this threshold easier to reach, allowing the reaction to occur at a faster rate. It's important to understand that what separates a catalyst from a reagent is that a catalyst is not consumed in the reaction. Previously, it was thought that there were only two kinds of catalysts: enzymes, which are made up of amino acids and can be found all over your body, and metals. List and Macmillan both reported independently of each other that small organic molecules can do the same job in reactions that are precise, cheap, fast, and friendly to the environment. So now that we have an understanding of what catalysis is, and more importantly, the distinction of organocatalysis, let's discuss the asymmetrical aspect of the discovery. There are many molecules that exist with the same chemical formula, but have differently arranged atoms. These pairs are called isomers, and more specifically, the ones we're interested in are called enantiomers, meaning they are non-superimposable mirror images of each other. Those are a few terms I just threw at you, but the important takeaway from this is the concept of chirality. The word chiral derives from the Greek word for hand, and it describes molecules as mirror images of each other in the same way that your left hand mirrors your right hand. Despite looking physically similar, chiral molecules can behave chemically different. One example is limonene, which you're probably familiar with and don't even realize. Here are two fruits you might recognize. You've probably eaten them before. Both contain the molecule called limonene, but the differences between them are enough to give the S-limonene molecule the scent of a lemon and the R-limonene molecule the scent of an orange. Our ability to distinguish between these two smells demonstrates the molecule's ability to behave differently depending on its structure. A more drastic example was observed in the 1950s when thalidomide was advertised as an over-the-counter drug to help treat morning sickness in pregnant women. The wrong isomer of thalidomide resulted in children being born with serious birth defects. This example stresses the importance of chirality in drug manufacturing. German chemist Benjamin List was studying a reaction known as the aldol reaction, a reaction constantly taking place in our bodies, facilitated by an enzyme called aldolase A. This enzyme is made up of over 350 amino acids, yet only 3 of them are responsible for the enzyme's catalytic activity. Dr. List's question was simple: are all these other amino acids necessary? List found that the same reaction could be catalyzed with just one amino acid, proline. Proline is extremely common, produced in the body, and used as a food additive. Using proline, the catalyzed reaction yields a stereospecific product, molecules that share the same handedness. In the US, David Macmillan was studying a reaction known as a Diels-Alder reaction. This reaction brings 2 organic molecules together to form a carbon ring. Carbon rings are everywhere in organic chemistry and in nature. This reaction is particularly slow and can be accelerated using a copper-containing catalyst. Macmillan identified that this catalyst was problematic because it contained a metal atom, despite being organic, and it was too unstable to be used in industry. Macmillan's question was, can I recreate this catalyst without the metal atom and with more stability? He discovered that a molecule called an imidazolidenone, say that 3 times fast, could catalyze the reaction, and like the reaction List was studying, Dr. Macmillan found that this catalyst exclusively produced molecules of the same handedness. Both men were not aware of each other's research and made their discoveries independently. Now here's the real kicker. These findings are being recognized for the 2021 Nobel Prize, but the discoveries actually took place in 2000. Since then, chemists have changed the way they think about constructing molecules. In application, organocatalysts are much more sustainable. One example is a molecule called oseltamivir, an antiviral drug used to treat the flu. The industry practice for synthesizing this drug requires 12 reaction steps. With organocatalysts, this number of steps goes down to 5, not only making the reaction more efficient, but also more environmentally friendly. Another example is a molecule called strychnine. Now, strychnine is actually a strong poison, and not something anyone really has any business manufacturing, but it has a complex structure, which can be used as a metric to compare its synthesis methodology. Using organocatalysis, the manufacturing of strychnine is over 7,000 times more efficient. In conclusion, the findings of List and Macmillan have given the gift of a new tool for building molecules to the scientific community. This makes organic reactions cheaper, environmentally safer, more efficient, and more precise. The pharmaceutical industry benefits greatly from this discovery. Well done, gentlemen.